just think about the sheer amount of software code being created every single day.
It's staggering.
And now, layer on top of that, this massive rise in AI tools just spitting out code like crazy.
Mm-hmm. At an unprecedented speed.
It really makes you stop and think, doesn't it? How do we make sure all this code, whether it's from a person or an AI, is actually good?
Right. Good meaning reliable, secure.
Exactly. Code that won't crash, leak data, or just become a total maintenance nightmare down the line.
Yeah.
So that's the puzzle we're diving into today, trying to establish some kind of fundamental benchmarks for code quality in this, well, whirlwind.
It's a huge challenge, absolutely. And in this deep dive, we're going to unpack a model that really tries to get into the nuts and bolts of what makes code genuinely high quality.
A structured way to think about it.
Exactly. A framework for those essential elements that make software robust and dependable.
And whether you're deep in the tech world yourself, or maybe you're just trying to understand the systems your company relies on, or honestly, even if you're just curious about how this digital world gets built, you've probably felt the impact of both really well-made software and, well, the other kind.
Oh, defo. We all have.
So let's jump right in. Welcome to this deep dive into building a standard model for software code quality.
And just before we get started, we want to mention that this deep dive is sponsored by Stonefly. They're leaders in enterprise storage, backup and disaster recovery, AI storage, and cloud solutions.
That's right. And if you happen to be looking for secure, ransomware-proof storage, Stonefly offers air-gapped and immutable options. You can reach out to sales at stonefly.com to schedule a demo.
Okay, so where do we begin? We're swimming in tools, methodologies.
Yeah, tons of them. But it feels like there isn't that one universal standard, that single ruler for code quality. Everyone's got their own slightly different take.
That's a perfect way to put it. And that lack of a kind of unified framework, it has real-world consequences.
Oh, yeah.
Think about software glitches taking down essential services, or the rising costs of just constantly fixing bugs.
And security breaches, exploiting badly written code.
Exactly. So the need for a more standard, more comprehensive approach is really becoming critical.
Okay, so this standard code quality model we're looking at proposes a way forward. It has 5 core parts. Let's start with the first one, readability.
Right.
Now, this sounds simple. Code should be easy to read, but what does that actually mean in practice?
Well, it's about making code that you can understand almost at a glance. And a lot of that boils down to consistency. Little details matter.
Like naming things.
Absolutely. Having clear, consistent naming conventions, like using Pascal case for interfaces and classes, which should usually be nouns.
Okay.
Then maybe lower camel case for objects, Pascal case again for properties. Methods should generally be verbs, constants. Uppercase.
Right. It seems small, but it removes that mental friction, doesn't it?
Right.
It lets you focus on what the code does.
Precisely. It reduces the cognitive load significantly, speeds things up, fewer errors. Then there's the visual structure.
Indentation.
Consistent indentation, yeah. Maybe just one tab. Sticking to a specific brace style, like Allman.
Allman, okay.
Yeah.
Where the braces line up vertically.
And keeping lines reasonably short, say 80 to 100 characters max.
So you're not scrolling sideways forever.
Exactly. It's like basic formatting hygiene.
It really is almost like the grammar and punctuation of programming. When it's consistent, your brain just parses it faster.
Spot on.
Right.
And then you have comments and white space used strategically.
Not too much, not too little.
Right. Comments should explain the why, especially for tricky parts, not just state the obvious. And white space breaks up dense code, making it easier on the eyes.
Helps anyone coming back to it later or a new team member, they can get the gist much quicker.
Definitely. Okay, so component number 2, maintainability.
Right. This is about making sure the software can evolve, right? Change over time without breaking.
Yeah.
Exactly. Future-proofing the code base, essentially. How easy is it to update or fix?
And a huge part of that is modularity, I imagine. Breaking things down.
Yes. Into smaller, self-contained units, each doing one specific job well.
That sounds like the single responsibility principle, avoiding those massive do-everything classes.
Precisely. Those monolithic classes become nightmares. Good modules help with maintenance, testing, even developing things in parallel.
Makes sense. Boosts efficiency, too.
And then there's reusability, designing code so you can use pieces in different places.
Cuts down on repeating yourself. Less code, fewer potential bugs.
Ease of refactoring is key, too. You need to be able to clean up the inside of the code, improve its structure without changing what it does on the outside.
Internal housekeeping.
Yeah. And finally, low coupling. minimizing how much different modules depend on each other's internal details.
How do you achieve that?
Using things like interfaces, dependency injection. The less modules know about each other's specifics, the easier it is to change one without causing ripples everywhere else. Ah, like building with Legos. You swap one brick.
Exactly. Swap one brick, the rest stays standing. It gives you flexibility.
Okay, that total makes sense. Pillar number 3, reliability.
Critical. Making sure the software actually works correctly and handles problems gracefully.
So error handling comes in here.
Big time. Using things like try-catch blocks to anticipate issues, giving clear, helpful error messages, not just error occurred.
Right, something that actually helps you debug.
Yes, and logging errors properly so you can track them down. Input validation is another cornerstone.
Checking the data coming in.
Rigorously. Is it the right type? Is it in the expected range? Using good libraries or rejects for this. It's fundamental for security, too, preventing things like SQL injection.
Where someone tries to sneak malicious code through an input field.
Exactly. Sanitizing inputs is crucial. And, of course, automated testing.
Not just the happy path, but the weird edge cases, too.
Absolutely. Got to cover those boundary conditions.
And reliability is more than just catching errors, isn't it? What about things like idempotency?
Good point. Idempotency, making sure doing the same thing multiple times has the same result as doing it once. Important for network requests, things like that.
And fault tolerance, like having backups.
Fallback mechanisms, maybe feature toggles, so if one part fails, the whole system doesn't collapse.
No.
And if you have multiple things happening at once, concurrency control, thread safety, using locks, synchronization to avoid data corruption.
Complex stuff.
Can be. And finally, good logging and monitoring, not just for errors, but for performance, usage patterns. It helps you spot problems early.
Right, before they become major incidents.
Yeah.
Okay, fourth aspect, efficiency.
And making smart use of resources. Performance.
So CPU, memory usage, speed.
All of the above.
Yeah.
It often starts with the basics. Choosing the right algorithms for the job, the right data structures.
Makes a huge difference.
Absolutely. And then careful memory management. Releasing resources when you're done with them,
Right.
not letting things leak.
Sounds important. What else?
Using asynchronous or batched I/O. Input-output operations can be slow, so doing them without blocking the main flow helps a lot.
Keeps the application responsive.
Right. And where it makes sense, using concurrency or parallelism to split up the work.
Speed things up.
Potentially, yeah. Caching's another big one.
Storing frequently used data somewhere faster.
Exactly. But you also need good strategies for invalidating that cache when the underlying data changes. Stale data is bad news.
True. Network stuff matters too, right?
Definitely for web apps. Minimizing network latency. Maybe batching requests together, using content delivery networks, CDNs, to serve content closer to the user.
And keeping an eye on it all.
Constantly. Regular profiling and benchmarking to find the bottlenecks. Where's the time actually being spent?
Makes sense. Even small optimizations add up.
Like lazy loading. Only loading resources when you actually need them instead of all at once up front.
Smart. Okay, last but definitely not least, security.
Absolutely non-negotiable today. Building software that can resist threats and protect data.
This needs to be baked in from the start, right? Not bolted on later.
Absolutely. It begins with that input validation and standardization we talked about earlier, preventing common web attacks.
Like SQL injection, cross-site scripting.
Yep. Then strong authentication and authorization. Who are you and what are you allowed to do?
Using standards like OAuth2, JWT.
Good standards, yeah.
Huh?
Plus strong password policies, multi-factor authentication wherever possible, layers of defense.
Okay. What about data protection itself?
Encryption is key. AES 256, maybe, for data at rest sitting in a database, and SSL TLS for data in transit moving across the network.
So it can't be easily intercepted or read.
Right. And secure error handling is crucial, too. Log the gory details internally for your developers.
But don't show scary, revealing error messages to the end user.
Exactly. Generic messages for users, detailed logs for devs. Secure session management is another piece using HTTP only. Secure cookies, expiring sessions, regenerating IDs.
To stop people hijacking sessions.
And fundamental principles like the principle of least privilege.
Only give the permissions absolutely needed, nothing more.
Correct. Keep your dependencies up to date. Scan them for known vulnerabilities using automated tools. Old libraries are a common entry point for attackers.
Good point. Like checking the ingredients you use.
Yeah. And finally, security-focused logging and monitoring. Watching for suspicious activity, failed logins, access attempts. But be careful not to log sensitive data itself. like passwords or credit cards.
Wow, okay. That's a comprehensive list. Readability, maintainability, reliability, efficiency, security.
That's the core of the model. And, this model wasn't just dreamed up overnight.
Right, it came from somewhere. How was it developed?
It involved a pretty thorough mixed methods approach. Started with a deep dive into existing research, looking at established quality models like ISO IEC 2501010,
Okay.
and also analyzing industry best practices. What are the big tech companies doing? What do respected guides like Clean Code or the Solid Principles say?
So building on existing knowledge.
Exactly. That initial work helped identify these 5 key attributes we just discussed: readability, maintainability, and so on, and figure out ways to actually measure them.
Turning concepts into something tangible.
Right. From there, the researchers actually built this structured model, defining the relationships between these attributes.
But theory is one thing. How do they check if it actually works in the real world?
Good question. It wasn't just theoretical. They presented the model to actual industry pros, developers, managers, architects, academics.
Got feedback?
Lots of feedback,
Right.
real-world insights. That led to refinements, making the model more practical, more relevant.
Okay, so expert validation. Then what?
Then they tested it empirically,
Mhm.
applied the model to actual real-world software projects, some new, some existing code bases.
So through its paces.
Yep. Collected data, got feedback from the teams using it,
Hmm.
both numbers and, qualitative stuff, what worked well, what was challenging.
And use that to finalize it.
Exactly. Integrated all those findings to make sure the final model was genuinely useful for development teams in their everyday work.
So how well was it received? Did they measure its impact?
They did. They surveyed about 100 people involved in software developers, PMs, researchers. The results were pretty positive.
Like what?
Well, for instance, 72% agreed that the readability guidelines really did improve code clarity significantly.
That's a strong majority. What about the other parts?
Similar story. 71% backed the maintainability practices, modularity, reusability.
Yeah.
Another 71% recognized how vital the security measures are.
Okay, solid support across the board.
And maybe the most striking number, 60%, 6 out of 10, rated the overall impact of the model on code quality as a 9 or a 10 out of 10.
Wow, that's quite an endorsement.
It really suggests that having this kind of structured, comprehensive framework can make a real difference in lifting the quality of code.
And when you think about how this connects back to you, the listener, even if you're not writing code daily, understanding these core ideas, readability, reliability, security, these are the things that make the apps on your phone work smoothly, keep the websites you use secure, and ensure the systems your company relies on are dependable. It affects everyone.
Absolutely. Which brings us neatly to a really hot topic right now, AI in software development.
Yeah, it's everywhere.
It really is. And the adoption rate is incredible. You see stats like, 83% believing it's essential to use AI to avoid falling behind.
That's huge. And we're seeing companies pop up specifically to tackle the intersection of AI and code quality.
Right, CodeAnt AI, founded pretty recently, 2023.
Right, by Amartya Jha and Chinmay Bharti. Already raised significant funding, impressive valuation.
And their whole focus is interesting. They're tackling that challenge.
Yeah.
How do you maintain quality when AI is turning out so much code?
So their platform uses AI to check AI-generated code, and human code too, presumably.
Exactly. The claim is it dramatically cuts down manual review time and helps catch bugs whether a human or an AI wrote them by over 50%.
That's a big claim. Manual code review can be a bottleneck, especially for big teams. It takes hours.
Their tech uses a language-agnostic engine, abstract syntax trees, ASTs, to understand the code's structure, the relationships within it. Supposedly much faster than manual review.
So it sees the forest, not just the trees.
Kinda, yeah. And it's not just theoretical. Apparently over 50 companies are using it already, including some big names.
Integrates with GitHub, Azure, DevOps. Supports lots of languages.
Over 30, yeah. And they even offer on-premise deployment for companies worried about sending their code to the cloud.
Interesting. It does raise that point, though. Maybe the human role shifts as AI gets better at writing code.
Maybe we become the quality gatekeepers, the quality engineers making sure nothing bad slips through, regardless of origin.
Yeah, ensuring it meets these standards we've been talking about.
It also connects to the whole challenge of scaling development teams. Companies grow, they need more engineers.
Why do they typically scale? More capacity.
That's one reason. But also diverse skills, fostering innovation with different viewpoints, delivering faster, allowing people to specialize.
Redundancy, too, right? Not relying on one person.
Better QA, responding faster to market changes. Lots of good reasons.
But just hiring more people isn't enough, is it? That can backfire.
Oh, absolutely. Scaling needs real planning. Clear goals aligned with the company culture. A roadmap. Thinking about infrastructure, architecture.
Streamlining hiring, too, getting the right people.
Crucial. Both hard skills and soft skills. Collaboration, communication, especially with bigger, maybe distributed teams.
Leadership development must become important, too.
Very. And effective agile practices, even across locations.
Yeah.
Don't forget product management. Either scaling often needs to be driven by product needs, not just tech. Short sprints can help keep things focused.
And underlying all that,
Yeah.
sticking to good coding practice.
Absolutely fundamental. Like the ones in this quality model.
Yeah.
And having a culture of always trying to improve.
It sounds complex. And now add AI into that mix.
Right. There's a lot of optimism about AI efficiency gains, faster cycles, more innovation.
But there are worries, too. Big ones.
Definitely.
Yeah.
Data privacy is huge.
Yeah.
79% concerned about AI accessing private info in some surveys.
Wow. And intellectual property. Who owns AI-generated code?
Yep. Nearly half, 48% concerned about that. And security vulnerabilities. Could AI actually introduce flaws? 39% worry about that.
It's telling that 40% of security pros think AI code generation will increase their workload.
It really highlights the need for human oversight, doesn't it? While AI might generate code fast.
Someone still needs to check it.
Seems essential. For errors, for security holes, for those tricky copyright issues, human expertise is still needed to ensure the integrity of the final product.
So, pulling all these threads together, the main takeaway seems to be that a structured, deliberate approach to code quality is just essential.
Yeah. Covering those 5 bases: readability, maintainability, reliability, efficiency, and security. It's how you build software that lasts, that you can trust.
And we really hope that you, listening, can think about how these ideas apply to your world. Even if you're not coding, you're interacting with software built on these principles or maybe lacking them.
It's about understanding what goes into making the digital tools we rely on dependable and safe.
Which leaves us with a final thought to maybe ponder. As AI gets deeper into software creation, how is our very definition of code quality going to change?
That's a great question.
And what new skills will we need to make sure this digital world stays secure and actually works?
Something to think about, definitely. Thank you for joining us for this deep dive.
And thanks again to our sponsor, Stonefly, a leader in enterprise storage, backup and disaster recovery, AI storage, and cloud solutions. If you're looking for secure, ransomware-proof storage, remember Stonefly sells air-gapped and immutable storage. You can contact sales@stonefly.com to schedule a demo.